Yeah, so you have 5 to choose from, pick 2.
Right.
Yeah. Yeah. All right, so question on homework number 11. And let's see, mine has a cosine inverse. What did yours have, Daphne?
It is the definite of 2 and then square root of 2 secant of 2 arc secant of x over x.
Okay, let me write that down.
2 minus.
So this is 1.10, 1.7, number 11, so the integral of negative 2
It's positive 2.
positive 2.
Wait, no. You're doing the problem. So it's negative 2.
Okay.
No, wait, positive 2. Sorry.
Jeez. Hang on a second. All right. So what are the boundaries? 2 to square root of 2?
2 square root of 2.
Or square root 2 square root of 2? Up to 2?
Yes.
Okay. So 2. We'll get there. 2 square root of 2. Up to 2, like that.
No, just square root of 2. 2 to 2.
Like that?
Yes.
Okay. And then this is a minus 2 arc.
Positive 2 arc secant
Positive 2 arc secant. Okay.
of x.
Positive 2 arc secant of x, and then that would be what? X square root
Of x squared minus
square root minus 1 down here. X. Okay. Ready to go?
It's just definition.
Okay, cool. Victor, are you doing it today or no? Okay, here is the no calculator part. Nope, that is Tyler's no calculator part. You want that one?
Sounds dusty.
Maybe. Okay, here's a blank no calculator part for you. Report back once you finish it. All right, so here we would do a U-substitution like we did the other day. So U is going to be the arc secant of x. So du would be 1 over x square root of x squared minus 1 dx. So then up here, we have our whole du right there. So that's du, and then u is just that right there. So when we reverse substitute, or we actually know regular substitute, we get the integral. I'm going to ignore the boundaries for a minute. From just 2u. U. Antiderivative of that would be u squared. This has boundaries, so I need to rewrite it or convert the boundaries. I'm going to rewrite it and then plug in. So that means I have the arc secant squared, let me come up in the right spot, of x from square root of 2 to 2. So now I have to figure out what that gives us. So remember, we always plug in the top boundary first, subtract, plug in the bottom boundary. So that integral should equal, let's switch to blue, the arc secant squared of 2 minus the arc secant squared of the square root of 2. And I think this one wanted an exact answer as opposed to a decimal answer, which means we had to figure out what the arc secant of 2 is. So if the arc secant of 2 equals something, it's an angle, which means the secant of some angle is equal to 2. Secant is 1 over cosine, right? So we could flip and say that means the cosine of some angle has to be 1/2.
1, 2 squared.
So I'm just I gotta draw a picture to double check. Cosine is an x value. So if x is 1/2, the angle should be pi over 6? No, pi over 3.
Yeah.
Pi over 3. Yeah, so the angle we want here must be then, according to this picture, if that's 1/2, it's the bigger angle over here, right, before pi over 2. So the angle I want is pi over 3. So we're gonna have a pi over 3 minus something. So the next part's pretty similar. I'm just gonna have a square root of 2 there, which is a square root of 2 here, which is a square root of 2 there. 1 over the square root of 2 is about 0.7-ish. So 0.7 would be over here, ish, right about there maybe, so that should be pi over 4. Yeah, so that angle is gonna be pi over 4.
And don't we have to square both of them?
Yeah, and I have to square them, thank you for reminding me. So the other angle is pi over 4, and then both of those need to be squared.
Okay.
Yeah, so I'm just gonna finish this up just for kicks. So that gives me pi squared over 9 minus pi squared over 16. So essentially I can pull the pi squared out and figure out what is 1/9 minus 1/16. Common denominator would be 9 times 16, which is what? 144?
Mm-hmm.
And then the new numerator here is 16, that's 9, 9 minus 16. 16 minus 9 is 5? No, 7?
7.
So then I get pi squared times 7 over 144 is the exact answer there. Oof, that was a trick for Calc.
I put pi over 3 back into the arc secant instead of taking it.
Yeah. Okay, I see. So you had the angle and the value were confused?
Yeah.
Okay. So we definitely need some trim there. On the test, you do not need to know the formula for arc secant, just arc sine, cosine, and arc tangent. All right, so moving on, what else should we do? Are there any particular questions on the take-home we should do, or the
For some
practice?
reason, I looked at 7, it doesn't
Yeah.
translate past that.
Yeah, Henry asked me about that earlier, about the late passes. Apparently, I forgot to push another button on some of them, so I pushed that button a few minutes ago, so you should be able to use late passes now.
Can we do a definite integral?
Yes.
And can you just go over the fundamental theorem stuff right at the bottom, just for funsies?
Sure. Okay, so fundamental theorem part 1.
I was looking at that and I was like, I don't.
So the fundamental theorem part 1 is basically about what I called the area function before. So you start off with some function little f of x on an interval, and you want it to be continuous. And then you create a new function. The book calls it capital F of x. I called it capital A of x in class because it's an area function. So that would be the integral from a to x of little f of t dt. So those two lines are the setup for it. Okay, so that's the premise. The conclusion of part 1 says that if you take the derivative of this area function, capital F, you get the boundary function, little f. So the rate of change of the area is the top curve, is what that says. So if I draw a picture of that, A, B, that's little f right there. If that's x, then, oops. Hold on. Capital F of x would be this area in there. So
So,
if it says the rate of change of the area is equal to the boundary function.
but is
So
that
this
where,
is part 1 right here.
is that where x replaces t in the function?
Here,
Yeah, because like at the bottom of it, like go to the bottom of the practice exam because it's different.
tools, I it's another one for you. I didn't.
That's
There you go.
helpful.
One second.
Yeah, so you want to.
I just got them on. Let me get Tour's test.
Are you sure you're not?
To same part 2. Print.
Okay, it's gonna pop up on the printer right now. There should be 4 pages with stuff on each side, and hopefully plenty of room for you to write stuff. Have fun. Oh, Vitor. No integral or derivative calculators. Only Desmos or GeoGebra or TI. Okay, and if your TI has integral capabilities, they're illegal. If your TI has integral capabilities, those are illegal.
You shouldn't be screwed.
I think he said I'm scared.
No, he said.
I think you said I'm screwed.
Oh.
Okay, so that's the fundamental theorem part 1. So Sam,
It's like I think it wants you to like at the like way bottom, like the last 2 problems on the practice exam.
Here?
No, way
down
here. Way to the bottom.
Yeah.
Oh,
so applying. Okay, so this
Yeah.
is a different question. So you
Yeah.
asked me to state it. So okay.
No, I meant apply.
All right, so let me do this, then we'll get to Carter's question. So, where's the? Okay, here we go. So again, the moral of the story is if I take the derivative of this function, I get that function. Right. So let's pick a function and plug it in there. So if I had the integral from a to x of, let's start off with an easy one, like the, I don't know, arc sine, oh shit. Arc sine t dt. And I gotta put a t here because I'm using x there for a different purpose. So this right here is my capital F. And so the fundamental theorem says if you take the derivative of your area function, it just spits out the inner function there, the integrand.
So you replace t with x, right?
Sine, and you just replace t with x. Why x? Because there's an x right there.
Okay, yeah.
This is why it's an x.
That's what I was confused about. I was like,
So sometimes you can use fundamental theorem part 2 to justify this. Fundamental theorem part 2 says if we just focus on this part and ignore the derivative outside for a moment, fundamental theorem part 2 says, do you know an antiderivative of that function? If so, you can use it. Do we know an antiderivative for the arc sine?
1 over the square root of 1 minus x squared.
Yeah, so it would be 1 over 1 minus, let's see, the square root of 1 minus x squared. Okay. And then it says, okay, now evaluate that at the endpoints, right? Which is going to give me 1 over 1 minus x squared in the square root minus 1 over 1 minus a squared over there.
But we don't need to prove it.
Okay. No, I'm just saying, I'm just going to compare fundamental theorem part 1 and fundamental theorem part 2. Part 1 says you can just jump right to that. Part 2 says you can use an antiderivative, but I've ignored this part right here. So now I put that back in. What happens if I take the derivative of all of this? What's the derivative of 1 over 1 minus square root of 1 minus x squared?
Arc sine?
It's the arc sine. And then what's the derivative of a constant?
0.
0. Yeah, so it just gets me back where I started. So the easier way is you just jump from there to there.
And then if it were an x squared.
Okay, so if you have the integral derivative with respect to x of the integral from any number up to x there, or let's say x squared instead of the sine, or arc sine again, I'll use arc sine, t dt. So the fundamental theorem says you got to have an x up there. If you don't have an x up there, then what you have is a chain rule, because you have a function within a function. So this is going to be the arc sine of x squared, yx squared, because that's the upper boundary. But the chain rule says you're taking the derivative of a function, so you better multiply by 2x. So the chain rule jumps in if there's anything but an x as the endpoint.
And so if it were a 2x instead of an x squared, it'd be the arc
There'd
sine
be
of 2x
There'd
times
be
2.
a 2.
Okay.
So other people didn't hear his question. If it were like the derivative with respect to x of the integral from a to 2x of, I don't know, choose a different function, sine of t dt, fundamental theorem steps in and says, oh, that's just the sine of whatever your top boundary is, 2x. But then because we're taking a derivative, the chain rule says, wait, don't forget to take the derivative of the inner function. And then the 2 pops on the end there. So now going to the actual problems I put on the sample test. The sample test, the first problem was take the derivative with respect to x of the integral from, I can't remember where I started. I started at 1. Look. 1, yeah. From 1 to x of the sine of t squared dt. So fundamental theorem just says, hey, rewrite that with an x. So that's the sine of x squared. And since that's just an x, I'm done. That's it.
That's the answer.
That's the answer for the first one. The second one, yeah, that's it. Fundamental theorem part 1 just says, hey, derivative and integral cancel each other. The second one says go from 1 to x squared, and here I have the sine of just t dt. And the only catch here is fundamental theorem says rewrite it as the sine of the upper boundary, and then the chain rule says, oh, but wait, what do I need to do next?
Multiply by the derivative.
Multiply by the derivative. Now, the chain rule is secretly acting up here. What's the derivative of x with respect to x?
1.
Doesn't change anything. So the chain rule is secretly always acting on stuff, but the derivative of x is just 1.
What if you had a t squared on the bottom and an x squared?
What if you had boundaries in both places?
No, I mean sine t squared on the bottom there. The t. Like the top has a t sine t squared.
Sine, oh, what if there were t squared there too? Okay. So that's another level of complexity that's not too bad, actually. So what if it was the derivative from 1 to x squared of the sine of t squared dt? The bottom line is t is just a place to substitute in whatever the boundaries are. So it would be the sine of something squared. What's getting squared?
X squared.
X squared. The inner function is the x squared here, so it would be just a 2x multiplier. Because that's what I subbed in. And that's what I need the extra derivative of. I'm not going to make the layer 3 deep like that. Worst I would do is 2 deep like the last one I did. Okay. Next. We have a request for a definite integral. Let's find a cute one there.
I think
They're all kind of cute.
22 is really cute.
22 is really cute. Okay, 22 is probably the hardest one here, so let's start with that one.
You know what? If we get it out of the way, you know.
All right, so then we'll do an easier one after this. All right. So this is pretty complicated. Most of the time when you see something pretty complicated, it's probably a U-substitution. That is the key. So usually with a U-substitution, we're looking for a function within a function. What is the candidate for a function within a function here?
Cosine.
The cosine of x, yeah. So that's where you start. Hope it works. Keep in mind that often when I do substitution, I make the wrong guess. It goes to hell and I have to try again. So du would be the opposite of the sine of x dx. Right? Derivative of cosine is negative sine. So up here, I like to underline stuff. So I have a sine, check. I have dx, check. I don't have the negative. So I think what I'll do for that is just throw the negative on the other side. So call it negative du equals sine of x dx. So that means it'll remind me to put that negative in there. And then my u is going to go in the cube there. All right, so rewriting this, I've got the integral, ignore the endpoints for a moment. I've got the u cubed, and then this stuff right here is a minus du. So I'm going to put the minus outside and du on the right. We have two options here. We can either find an antiderivative, substitute back, and then use the boundaries, or we could change the boundaries. Does anybody have a preference?
Substitute.
Change the boundaries. Okay, we have two different views on it. Just for fun. If you're going to substitute boundaries, now is the time to do it. So you have x versus u. If x is 0, what's the cosine of 0?
2.
Nope.
Just kidding, -1?
Positive 1. Good job. Yes. So making a sketch of the cosine or whipping out your calculator is not a bad idea. This is the cosine at 1. Let's see. Pi is right here. Pi over 2 is right there. So pi over 2 cosine is
0.
0. So that means I am integrating from 1 to 0 if I leave the u's in there.
And sine starts at 0, right? Not
Sine
1.
starts at 0 and climbs
Okay,
up.
okay.
Yeah.
So that-
All right, antiderivative for u cubed. U, 1/4 u to the 4th, yeah. And then we have a negative in there. I'm going to throw the negative on the outside for now. And then I'm going to go from 1 to 0. Notice the order here, they're not in their normal order. So I want the opposite of 1/4 0 to the 4th minus 1/4 1 to the 4th. So that means I want the opposite of negative 1/4, which is 1/4. I'm going to do this the other way just to check. Highlight. Because that's what the substitution said. If I plugged in x equals 0, it translates to u equals 1. So I have to replace x equals 0 with a u equals 1. And then at the top I had pi over 2. Pi over 2 has to replace with u equals 0. So since the pi over 2 is the top, 0 is going to go at the top. Yeah. So if the jumping around boundaries bugs you, then here's your alternative.
But like once you've done that, you don't have to plug x back in.
You don't have to plug x back in if you switch boundaries, yes. That's the benefit. If you don't like that, then your alternative is to, let's see, pen, yeah. I would rewrite this as, like I did before, the opposite of u cubed u. Antiderivative would be the opposite of 1/4 u to the 4th. And then I got to reverse substitute. So now I'm going to change color. Substituting back, I get 1/4 of the cosine of x to the 4th. Now that I put
Negative.
the x stuff back in, negative, thank you, I can put in the 0 to pi over 2 and then go from there. So I've got the opposite of 1/4 of the cosine of pi over 2 to the 4th minus 1/4 the cosine to the 4th of 0. And then I have to figure out what's cosine of pi over 2. What's the cosine of 0? What's the cosine of pi over 2? This becomes 0. What's the cosine of 0? The 1. 1 to the 4th is 1, times 1/4 is negative 1/4. I want the opposite of that. So I still get the opposite of negative 1/4 or 1/4. I tend to do it this way and not translate boundaries. I find my antiderivative, I reverse substitute, then I plug in the original boundaries. This is the way I usually do it. Turns out there's another order of operations on this. Okay, another. What else looks like fun?
There was the definite integral of sine x over cosine x. And I could figure it
The
out.
indefinite integral?
Or the indefinite,
It's just
yeah.
the integral. I'm going to do one more definite integral, and then I'll do an indefinite. Carter, you asked what looks good to you.
Any of them.
Any of them. Okay. How about 18?
Okay.
All right.
That looks good.
So let's copy. And on every one of these, notice back here, I'd say for 23, graph one of these and shade the area, see what it looks like. It's not a bad idea to do that on every one of these. You gotta run?
Yeah, my practice time got moved up.
Okay, good luck, have fun. It's a good day to practice.
See you on Monday.
New page. Okay. So on this one right here, I'm actually going to graph it right away. I would highly recommend when you're taking a test, you've got this amazing graphing utilities, use them. I'm going to use GeoGebra today. And what was that? A 4x, where'd you go? Minus x squared. So f of x equals 4x minus x squared. And I am integrating from 0 to 4. Oh, that's beautiful. I'm looking exactly inside this hump here. Cool. So here comes the work to go with it. So I'm just going to draw my rough sketch and do my work. Let's see what's over here. There's 0, there's 4. This goes up, comes down. So we are finding this area right here. I think this one's pretty straightforward. I'm going to have 4 times the antiderivative of x, which is x squared over 2. Now, a lot of you will be tempted to think that's 1/2 x squared and half of 4 is 2. Write it down on the test. The more you do in your head, the more you leave yourself room to make errors. Writing it down allows you to confirm your belief. Minus 1/3 x cubed from 0 to 4. Plugging in, I'm going to have a 4. Actually, I'm at a point where I can reduce that. Let's call that a 2 now. 2 times 4 squared minus 1/3 times 4 cubed minus parentheses 0, 0. For me, it's usually worth writing that down and confirm to myself my belief is right. Sometimes I even write more detail. I rewrite all of this with the 0 for x. In other words, 2 times 0 squared minus 1/3 0 cubed. All right, so I believe that is definitely 0, so then I just have to clean this up. 16 times 2 is 32 minus, is that 64?
Yeah, 64.
64 thirds. Common denominator would be 3. 3 times 32 is 96. Which gives me 32 thirds. If you like mixed numbers, which aren't bad at this point, what's that going to be? That's 10 2/3. So circle one of those as your answer. What else could I do to check?
What's the antiderivative table?
I could take the derivative and see if it matches. Yeah. The other thing I could do is just ask Desmos to draw a bunch of rectangles.
Or
Or
can you just,
GeoGebra, sorry.
can you just ask Desmos to
Do a numerical
integrate?
integral.
Yeah.
Yeah, it has a function called n integral. So I just say, hey, grab f of x, go from 0 to 4, and it says 10.66666666. Now, you could certainly just go straight to that and write only 10.66666666 GeoGebra. I will give no credit for that. None. Okay.
Not even for the right answer.
Not even if, even if you look at that and say, yeah, that's 10 2/3. So if I see only this in 10 2/3, it's a 0. Okay. I want antiderivatives evaluated. All right, next. Sine over cosine. Let's try that one. So this one is a indefinite interval, excuse me. So don't forget your plus c's. So we want the integral of the sine of x over the cosine of x dx. So this is a complicated function right here.
Of tangent.
You could just say it's tangent x, and maybe you remember the formula for tangent. I remember the formula for tangent, so you could just write that down. So one possible solution here is you say, hey, I know this is the integral of the tangent of x.
Does that
Of x. Plus c. So if you remember that, cool, write that down. If you don't, the alternative is a substitution.
wait? Okay.
So I'll prove that's true by using a substitution. Any recommendations?
Is it a secant squared?
Nope.
Okay, yes, Joe.
Okay, that's all right.
You could substitute cosine for u.
Yeah, since cosine's in the bottom, it's the function within the function. Yeah, so I would let u equal cosine here. Worst case scenario is you pick u equals sine and it doesn't work, and you try again. Du is equal to negative sine of x dx. And by the way, how do you know if it doesn't work, the substitution? You end up with something worse than what you started with. That means it didn't work. The substitution is supposed to make it simpler somehow. All right, so what do I know? Let's see.
Do you want to bring up the negative?
What's that?
Do you want to bring up the negative?
Yeah, I'm going to put the negative with the du in just a sec. But first, my first step is just kind of highlight, is this going to make my life easier? Ooh, there's my du. I like that. And then I'm just going to take that negative and put it over on that side there. And then again, I have my u right there. So this translates as the integral of -1 over u du. If you want, you can pull the negative out front. So if I pull the negative out front, what's an antiderivative for 1 over u?
Negative ln.
The natural log of the absolute value of u. Okay. Taking this a little further, I can write that as the opposite of the natural log of the absolute value of, what is u?
Cosine.
Cosine of x. And you might say, hey, that doesn't look like what you have up there.
Oh, but then you can put the
Logarithms have a
negative,
property that says if you have a negative multiple, you can bring that in as a power.
and that
Negative
would
exponent
be
means
on there.
flip the base. So that means what I really have here is the natural log of 1 over cosine of x when I bring that -1 in as a power. And 1 over cosine of x is really secant, which was what I had memorized.
Because okay, so
Right?
I put that into a derivative calculator to like find that out, and I could always get to the negative ln cosine
Yeah,
of x,
and-
but I could never.
Some
I know.
integral and derivative calculators will say, hey, the answer is natural log of secant. Others will call it the opposite of the natural log of cosine. It just depends on what derivative calculator, integral calculator you choose and what you tell it. All right, so by the way, if you had said this was your answer, I'd be perfectly happy with that. If you did that, you just stop right there. That's cool. It's a great answer. You don't have to take it that extra step necessarily. All right, we got time for a couple more. See, we did this problem together yesterday, the day before we started it. We could do a net area versus total area problem.
Yes.
Do that one? Okay, let's take, did we start this one in class yesterday? We started it, but we didn't finish it. I just talked about it. Yeah, let's do this one. All right, so starting over on that sucker. Screenshots. Just gonna grab this. I need the function and the interval. Okay, so graph it. About your calculator, graph that thing right there. So let's see, we have x cubed minus 2x squared minus x plus 2. Get this stuff out. So f of x equals x cubed minus 2x squared next minus x plus 2. Minus x plus 2. Okay, so here's my function. And then I want, okay, there we go. I want to go from x equals with a -1 all the way, I think, to x equals 3, right? And one thing I like about GeoGebra and Desmos is I can have it draw those horizontal lines, x equals this, x equals that, so I can see where I'm working. So I have this positive hump, I have this negative hump, and then I have this positive section over here that I'm looking for. Tyler, you done?
Yeah, but I realized I messed up on first part.
Oh.
Accidentally did the
Definition of the definite rule. Oh, should we talk about that?
That's why I wasn't.
Sorry.
Nobody Thank you.
Blah, blah, blah. Okay. So, yeah.
Sick. So disgusting.
Yeah. Yeah. That's what I was hoping for. Okay, so let's do it. First one's pretty easy. The first question here is just find the net area. So part B, once we get the graph, your best sketch. And net area is just a straight integral from -1 to 3 of your function. So we just find an antiderivative and plug it in. Have a great day. So antiderivative of this thing would be x to the 4th over 4 minus 2x cubed over 3 minus x squared over 2 plus 2x. And then we just evaluate at -1 and 3. Let's see what we get when we do that. And at this point, I would plug it into my calculator, focus on the decimal, otherwise we'll clean it up with fractions. I think this is going to be decimal-like. Yep. All right, so maybe I'll just do a little fraction work here quick. Page. All right, so what do I get? I get 3 to the 4th power is 81. The cube is 27 times 2 is 4/3. E squared is 9/2 plus 6. And that I'm going to minus positive 1/4. A negative cubed is a negative, and I'm subtracting that, so that would be a plus 2/3. Squared, that's going to stay minus 1/2, and then minus 2. And definitely use your calculator to check. All right, let's see. 81/4 minus 1/4, that's kind of a nice common denominator, would be 80/4. And 84 is what, 20? 54, negative 54/3 plus 2/3, what's that mean? 50, negative 52/3. That doesn't clean up very nice, does it? It gives me 52, 17 1/3 times. Negative 9/2, ooh, I made a mistake. That's not right. Each of these needs its sign changed. That would be negative 54/3 minus 2/3, 54, 5, 6, 56/3. Here's 56 times 18 times with 18 is 54, 2 left over. All right. Negative 9/2 plus 1/2 is minus 8/2 minus 4. 6 minus negative 2 is 6 plus 2 for 8.
I need a new pen.
Okay, go for it.
My God, scared me.
All right.
You got
All right.
this.
So.
Got a minute.
All right, what do I get? 20 minus
28 minus 18.
20 minus 18.
Just
negative
plug it into a calculator.
I don't like calculators. I want to use calculators.
6.
1 1/3 plus 4. I get 5 1/3.
Looks like it's 50.
So I highly recommend plugging this straight in your calculator and make sure you get 5.33333.
Are we allowed to use a calculator more than you do on the test?
Yes,
Like,
but if I'm wanting exact answers on each of these. So if you tell me the
Oh.
answer is
So,
7.23456,
So like on the trig ones, I have to,
you have to do trig.
okay.
Like the cosine
Uh-huh.
of pi over 2 equals whatever it equals.
That's not horrible, but.
All right, so
good.
real quick before we close up here, total area. Does everybody remember what total area means?
So every point, every point it dips and changes sign.
The absolute
God, that's so
value.
Absolute value of p-vex. Yeah, so any place it changes from positive to negative, you got to take its absolute value. So for this function, it went up, it came down, it went up again. I think it was something like that-ish.
You would
No.
pretend as if the
No,
curve
it hits
right
at
there
negative
went
1
like
at
that.
0, and then it hits at 1 and then 2.
Pretend it
and then
didn't go
goes
over
up.
Yeah,
it.
you would make it pretty much just go like that.
Yeah.
So then we would have to integrate from here to here. So
And
what is
then-
that, from -1 to 1?
One.
And then this over here is 2? Yeah. So you would have the integral from -1 to 1 of just the regular function.
Then plus.
Absolute value says then you have to take the opposite of any negative section. So you want the opposite of the integral from 1 to 2.
Couldn't you say plus the absolute value of that?
You could do plus the absolute value.
But
yeah.
you're missing a point, unless you're, oh no,
I'm
you're
not
not.
done yet.
Yeah.
So that gives me, I've got this, I flip that by taking the negative, and then I add on the integral from 2 to 3. That's positive, so I can just do regular p of x there,
See.
and then a plus. So I have to do each of those separately.
Wait, so you subtract the opposite, or is that
Yeah,
negative
because this
the
is gonna give
opposite?
me a negative area, so this says take the opposite of that negative area. It
Okay.
makes it positive.
Yep.
That's what the absolute value tells us to do.
Okay.
So you gotta look at the graph. If
Put
it
it on the
says,
thing, forget everything.
if it says total area or total change, total distance, something like that. All right, post questions if you have them. I'll be checking the forum this weekend.
So displacement is, net area?
Displacement is net area. Yeah.
So if if one of the areas is 1 and then the other area is -1, the total distance would be 0.
0. No, the net,
Or the
Distance would be
net, the
0.
net would be 0,
the
the
total
would
distance
be
would be
2.
2.
Okay.
Oh, okay, I had
Yes.
it backwards.
Yeah, so as far as,
Okay, so I.
So the total should be like bigger than the net.
total is always bigger than the net.
Okay.
Yeah. Well, less than or greater than or equal.
Yeah, yeah, yeah.
If there's no negative areas, they're the same.
Okay.
So, yeah, so what Sam was saying is displacement is net area or net change. And then total just means you have to use the absolute value of the function.
I'm feeling a little better about this test. Still hurts, but a little bit less.
Yeah, this is tough stuff. Have a good day. You too. Dylan, how you doing?
Good.
Yeah?
I was gonna ask, are we gonna get those formulas from 1.6 and 1.7?
The only formulas I'm going to give, turn that off, are the ones about summations. So, let's see, 1.6, what's 1.6 and 1.7? You have to, so you have to know integrals.
Those
So-
ones, like the
So
one-
you need to know the integral of e to the u du, z to the u. I told everyone I'm not going to test on the integral of natural log because we're going to go over that in more detail later. So the other ones you need to know, integral of 1 over u du. You do need to know that's the natural log of the absolute value of u. And then you don't need to know all the formulas in 1.7, but you do need to know the ones for arc sine.
There's only like 3, I think.
There's only 3 you need to know, yeah. So if you take 1 over the square root of a squared minus x squared dx, then that is equal to the arc sine of x over a.
It's U, isn't it U squared?
Yeah, they usually put a u there. U, and then if you put a minus here, it's just the arc cosine, so that's no big deal. Or you can call it the negative arc sine, right? So the arc cosine is kind of worthless. So the other one would be 1 over x squared plus 1, or 1 plus a squared.
U
U.
squared plus A squared plus U squared.
Yeah, because it's a plus, the order doesn't matter. U, that would be the arctangent of u over, no, that would be 1 over a times the arctangent of u over a. Yeah, this one gets a 1 over a, that one doesn't.
Yeah. Most of the time it's just 1 over 1.
Yeah, most of the time it's a 1
Yeah.
for a. And then, other ones you need to know, sine would be a good one to know, cosine, you need to know power rule. You don't have to know tangent, but like that problem we just did is not a bad one to have memorized.
Are you talking about like U to the R plus 1 over R plus 1? We don't need to know that one?
Yeah, so if I say, yeah, if we call that R as the power, then that would be U to the R plus 1 over R plus 1. Yeah, you need to know that. Tangent's optional, but you definitely want to know sine and cosine.
Is there anything else I'm missing? I think those are the big ones.
Yeah, those are the main ones you need to know. Question? Oh, you can take a picture of that?
Yeah.
Yeah. So, yeah, between now and Monday, write those down 3 times a day.
Well, like at the
So
beginning
you'll
of
have
homework,
muscle memory and burn
at the
in your
beginning of
mind.
homework, I didn't really know what I was doing because it was just hard.
Yeah.
Like, using U and all that.
Yeah.
And then like towards the end, like it was easy.
You just, yeah, once you get used to them, it's
Yeah.
not that bad.
Are you around this afternoon?
I am stuck in meetings all day.
Okay.
Yeah,
So just post questions then?
yeah, post questions if you have them.
Okay.
Yeah,
See ya.
sorry.
Thanks. I'm booked in.
Yep.
For best.
That's correct. Oh, and then you plugged in, okay, so maybe you have, all right, so let me.
Because I thought the computer was, the third of parentheses, I thought the computer would plug it, or just the, I thought it would distribute the negative for me.
Yeah, it
Here you
should.
go, Gary.
I just got like 26 instead of the U-Subs.
Okay, so this should be a 4 over here, so you have a typo right there. You have a 2 on the bottom. So that should be
It's going fast.
4 down there. 3. How you doing, Sarah?
I finished.
Good job. 2 times 3 is 6. Okay, that looks good. And then this one, negative, 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 negative. Okay. And then you get.
That fixed it.
Oh, it's close. You got 5 and that's like 5, 6. So either I have a mistake or you have a mistake. Okay, I'm gonna show you a trick to help evaluate that. So type g of x and let g of x be the derivative. So then I'm just gonna type x.
Can you just
Get this
do it
down so I
prime?
can type. I don't-
I've used that. for
it does do
before.
that?
Mhm.
Shit, that's not good. Oops. Oh, geez, it does f prime. It's not good. So then I could just, oh, no, I don't want f prime.
That prime of
We want the integral. Yeah, I won't do that. I want the antiderivative, not the derivative. So I'm gonna call the antiderivative g of x. And then I'm just gonna type in what I wrote on the board. So x raised to the 4th over 4 minus 2x cubed over 3. So this way I don't have to worry
I've
about.
done that before. but
Yeah,
not
so it just
with
makes the typing
derivatives.
easier. Yeah, so you can use it for antiderivatives. It makes life way easier. Squared
Then you'll just do G of
over 2. Then you would just do g of 3 minus g of negative 1. So then plus 2x.
make it hard to make mistakes too.
So g of 3 minus g of 1. And we get 5 1/3. Yeah, so there must be another error up there you and I aren't seeing. Cubed over 3. Squared over
Is it the way?
2.
Could be the way I wrote these.
Oh, yeah, so notice your 3 is outside the power there. That 4 should be outside the parentheses, I mean. So you type this one on. Fourth power should be out here. Now they match. Yeah. Yeah, so that's a nifty trick there. So,
Okay, I'll do that. Just want to make sure I can get it right on the text. I also have the first calculus, chemistry test on Monday.
oh yeah. How's chemistry going? It's rough.
I don't know, this term's weird. I just feel like I'm behind, but I'm doing a lot of homework, but it still feels like it's just a lot more time, I guess. I need for this term than last term. Everything. I need more hours in the day.
Me too. Or we need a mini me that we can trust to do stuff just like we would.
Yeah, plug them into our brain.
Not get twice the power. All right, yeah, have a good weekend. Oops, I still brought